Hello friends of the Thermo channel. Today I'm using a yellow shirt because I'm going to talk about something that Brazilians like me treasure a lot, the Brazilian national football team. Every 4 years, Brazil goes to Bolivia to play for the World Cup qualifiers, and these matches normally take place in the city of La Paz, the highest capital city in the world. Every time this happens, the press talks a lot about the effect of high altitude on athletes' performances. What we are going to do in today's problem is to use the principles of classical thermodynamics under a set of assumptions to have an idea of the kind of conditions that the players face when they go to La Paz. This is a beautiful application of classical thermodynamics that I invite you to follow with me. Here is the problem. Brazil's national football team departs from Rio de Janeiro at sea level to play Bolivia in La Paz, 3,640 meters above sea level. In Rio de Janeiro, the atmospheric pressure is equal to 1.0132 times 10 to the power 5 Pascal, and the mole fractions of nitrogen and oxygen are equal to 0.79 and 0.21 respectively. We will consider that the atmosphere behaves as an ideal gas binary mixture in equilibrium at the constant temperature of 20 degrees Celsius. The goal of this problem is to find the atmospheric pressure and the mole fractions of nitrogen and oxygen in air in La Paz. Let's discuss some background information, the first of which is that the chemical potential of a component that's free to diffuse within a system will be uniform throughout the system at the equilibrium state. The second piece of information that's relevant here is the fact that chemical engineers often neglect the effect of gravity in their equilibrium formulations. However, we cannot do this here because the difference in altitudes between La Paz and Rio de Janeiro of 3,640 meters is pretty large. Let's now move to some background information about thermodynamics. The chemical potential of a component is its partial molar Gibbs energy given by equation 1. And the Gibbs energy is defined as U minus Ts plus PV, where U is the internal energy, T is the temperature, S is the entropy, P is the pressure, and V is the volume. Because the height will play such an important role in formulating this problem, we'll define an extended Gibbs energy as the conventional Gibbs energy plus the potential energy of the system. And the potential energy will be the product of the total mass by the gravity acceleration g by the altitude h. The total mass will be the summation of the component masses, and each of the component masses will be given by the number of moles times the molar mass of that component. We can then derive an expression for the extended chemical potential, which will be the partial molar extended Gibbs energy. The extended chemical potential will be equal to the conventional chemical potential plus the product of the molar mass times the gravity acceleration times the altitude. The expression for the conventional chemical potential of a component I in an ideal gas mixture appears in equation 7. The first term on the right-hand side of this equation is the chemical potential of the pure ideal gas at the system's temperature and at a reference pressure P0. Equation 8 shows the expression for the extended chemical potential of component I in an ideal gas mixture. Observe that this equation accounts for the effect of gravity through its final term mgh. Next, we apply the extended chemical potential to formulate our equilibrium problem. The extended chemical potentials of nitrogen have to be equal in Rio de Janeiro and in La Paz, and the same should happen to the extended chemical potentials of oxygen. In these equations, the superscript Rj stands for Rio de Janeiro and Lp for La Paz. If we substitute the expression for the extended chemical potential in the equilibrium condition, we find equation 11. After some simplification, equation 11 leads to equation 12. After some additional manipulation and applying exponential to both sides of the equation, we obtain equations 13 and 14. Their left-hand sides are the partial pressures of nitrogen and oxygen, respectively. Adding these partial pressures, we can find the pressure in La Paz, as done in equation 15. All the symbols that appear on its right-hand side have known numerical values. They appear here: the gravity acceleration, the universal gas constant, the molar masses of nitrogen and oxygen, the temperature, the pressure and mole fractions in Rio de Janeiro, and the altitudes of La Paz and Rio. Using these values, we find that the atmospheric pressure in La Paz is equal to 0.664 times 10 to the power 5 Pascal, which is about 66% of the pressure in Rio. Equations 17 and 18, which are derived from equations 13 and 14, give the values of the mole fractions of nitrogen and oxygen in La Paz. The value for nitrogen is 0.8 and the value for oxygen is 0.2. The mole fraction of oxygen in La Paz, 0.2, is smaller than in Rio, which is 0.21. This happens because the molar mass of oxygen, 32 grams per mole, is larger than the molar mass of nitrogen, which is 28 grams per mole. In this way, the spatial distribution of oxygen is more sensitive to the effect of gravity than the spatial distribution of nitrogen. It's interesting to calculate the ratio of the oxygen partial pressures in La Paz and in Rio de Janeiro. According to the calculations of this problem, it is about 63%. This means that the amount of oxygen available to a football player in La Paz is about 63% of the amount available at sea level in Rio de Janeiro. So if you ever land in La Paz and get an invitation to play a football match with your local friends, think twice. It's not that easy. Bear in mind that the formulation we developed has applications well beyond those that were discussed here. In the oil and gas industry, people talk about compositional grading, which has to do with the fact that within an oil reservoir, the composition depends on depth. Thank you for watching this presentation. My name is Marcelo Castier. Goodbye.